Hello, welcome back. The title of this lesson is called Projectile Motion Problems. This is part 1. So in this lesson, we'll solve our first problem. And the first order of business after we read the problem is to actually write down the equations of motion. And then we're going to consider the horizontal and the vertical motion, or the horizontal and the vertical motion, to be separate and basically totally separate entities. And then we'll kind of walk through how to get to the answer of the question. So the problem says a ball is tossed with an initial horizontal velocity of 5.0 meters per second from the top of a 20-meter building. And we have 4 parts. First part, sketch the path of the trajectory of the ball. Next part, make a graph of the x component of the velocity as a function of time. Part C, make a graph of the y component of the velocity as a function of time. And D, at what distance from the foot of the building does the ball land? My advice: most physics problems and also chemistry problems will have A, B, C, and D. Try to ignore anything other than part A. Because usually when you find part A, it really helps you understand how to attack the rest of them. So the first part says we're going to throw a ball, have a horizontal velocity, building is 20 meters tall. Part A, sketch a path of the trajectory of the ball. And not only do we want to sketch it, we want to try to understand a little bit more about what it means. So let's do an initial sketch, which will not be very accurate, and then we'll kind of like fill in the blanks a little bit later. So basically we have some sort of building here, right? So I'll go and put a little building right here. And at the top of this building is someone who is throwing a ball. We don't need to put the person or whatever, but we have a little ball here. And it's going to be initially launched this direction with V naught horizontally only 5.00 meters per second. So if we throw a ball, and remember, we're only throwing it horizontally, what is going to be the path of that ball? Well, it's going to go kind of sideways and then begin to fall, and then it kind of turns into something like this, and it's going to hit eventually the ground and crash into the ground like this. So technically, we're done with part A because it says sketch a path of the trajectory. Now, you're doing this from your experience. You know when you throw things, they kind of make this curved path to the ground. But we want to go a little deeper. We actually have the math that tells us the velocity and the position of the ball. How can we more fully understand, or how can we prove to ourselves that this really is a quadratic shape? Quadratic meaning a parabola, an upside down parabola, right? So the first order of business that I want us to do together is I want to write these equations of motion down. And we're going to do it so many times that you're going to get good at it. So let's get comfortable, and we're going to write these equations of motion. I'm going to put them right over here on the side of the board, and then we're going to use them. The first one, this is the way I want you to write them. V is equal to V naught plus the acceleration times the time. Now notice I didn't put any x's or y's in here, and that's because this equation applies to the x direction. If you put the x acceleration direction and the x final velocity and the x initial velocity, this applies in the x direction, but it also applies separately in the y direction, where a would be replaced with minus g, which is the acceleration of gravity. But this is the general form of the equation. Equation number 2 is x is equal to the initial position, x naught, plus v naught t plus 1/2 times a times t squared. Now in this one, I had to put x's because I have to put something for distance. But I want you to remember that this equation applies to the x position and also to the y position. If I put y's in here and replace this with the initial value of the velocity in the y direction and the acceleration in the y direction, negative g for instance, then this equation applies as well there. Now you can combine these two equations here and get a very useful equation. V squared is V naught squared plus 2 times whatever the acceleration is times x minus x naught. X minus x naught is just the distance it's traveled, delta x in other words. And this equation comes from the other two. I recommend that you always write your equations down at the beginning of every problem, because every projectile motion problem will use these equations. We have to apply them in the x direction and apply them in the y direction, but we're going to use them. So just write them down, and I'm going to write them down too, and that's going to help you remember them because you're going to see me write them every time, and you're going to write them yourself every time. So we know the ball is going to do something like this from experience. We didn't write it down initially, but we know that this building has some height to it, and it says it's, 20 meters, so 20.0 meter tall building. But we don't know how far away it lands. That's one thing we want to calculate. And we want to do some graphing and all this other stuff. But in the beginning of the problem here, let's figure out a little more detail as to what the shape of this looks like. Let's prove to ourselves that it really is a parabola upside down like this. So how would we do that? We want to trace out the position of the ball as time goes on. right? So let's look at the x direction only. And then after we do that, we're going to look at the y direction. That's what I told you we would do at the beginning of every problem. Consider each direction separately. So if you look and apply the position of the ball, this equation relates the position, and this equation relates the velocity of the ball. We don't care about the velocity. We want to know the trajectory of the ball, the position. All right? So we can just put this equation in the x direction. And the way we would do that is x is equal to x naught plus v naught in the x direction times time plus 1/2 at squared, right? But there is no acceleration horizontally, so actually I don't even need to put this term at the end. You can just basically write this term as it sits. But since this is our first problem, we'll just go ahead and put it 1/2 a, whoops, not 1 over a, 1/2 times a times t squared. So this is the initial equation. All I've done is I've put this in place. V naught is now in the x direction. The acceleration is, I didn't write it down, but it's in the x direction as well. Now let's rewrite this in terms of what we actually know. So what we know is that the ball starts at an initial position up here at the top. If we kind of make a coordinate system like this is a y-axis here, and then here is the x-axis here, then the origin is basically right down here. This is the origin. So what is the initial position of x of the ball? In the initial position of x, if this is the origin at the edge of the building, then right here, the initial position, the coordinates, if you want to think about it this way, is 0, 20. 0 in the x direction and 20 meters up for the y direction, right? So the initial value of x is actually 0. So we could actually just put 0 in there. So we could say x is going to be equal to 0. That goes in right there. What's the initial value in the x direction? The initial value of velocity in the x direction is 5. So I'll put 5.00 times t, right? We just put that in right there. And then 1/2 at squared. We have 1/2. What is the acceleration in the x direction? 0. So what we actually get is 5 times t. I'm just going to drop the decimals. 5 times t. And we have 0 here and 0 here. So you see, you don't have to memorize and say, oh, this makes sense, or this makes sense, or that makes sense. You just write down the equation of motion and you put in what you know. Since it starts at an x location of 0, this goes to 0. Since the initial value in the velocity in the x direction is 5, that goes there. Since there is no acceleration horizontally, we put a 0 in there, and the equation we get out of it is this. So what this is telling us is that the position in the x direction, the x coordinate, as time goes on, is just linear in time. It's linear in time. And what I mean by linear in time is as 1 second goes by, I'm 5 meters away. 2 seconds goes by, I'm 10 meters away. 3 seconds go by, I'm 15 meters away. So as every second that goes on, it's just a straight multiplication. That's a graph of a line, basically, and that's just linear in time. And that's because gravity is acting down. There is no force or any acceleration going on this way. As time goes on, I'm just kind of cruising along in this direction. Now, I said I was going to do the y direction over here, but actually I lied since I ran out of room. Let's go and do the y direction down below. Let's do the y direction down below. So now what we have to do is we're going to rewrite this equation in terms of y. So what it's saying is the final position, in this case we're talking about y, is equal to the initial position of y. So y is equal to y naught. And then this is the initial velocity in y. So this is v naught t in the y direction, v naught yt. And then we have plus 1/2 at squared, plus 1/2 a times t squared. So it's the same thing. We just put the positions in y and the velocities in y and everything else, and we know that this is going to be gravity. So when we make those replacements, what we're going to figure out is that the initial position of y is, notice the initial position starts at the top of the building at y is equal to 20 meters. So 20 goes into the initial position for y. That's very important. What's the initial value of the velocity in the y direction? Well, I was kicking it only horizontally, so I gave it 5 meters per second this way, but there is no horizontal or vertical component of velocity. I'm just essentially, the ball is not initially moving in the y direction, so this becomes a 0. So 0 times time, right? And then plus 1/2 at squared, I'm going to change it to minus 1/2 times gt squared because g is gravity. And so minus 1/2 gt squared. All right, so what I'm going to have here is 20. This becomes a 0 minus 1/2 9.8 t squared. So what I have here is 20, and then we have minus 1/2 times this becomes 4.9. 4.9 times t squared. So we have 20 minus 4.9t squared. Now, what are the units we have? And first, before we get into the units, how does this look different than here? In the x direction, we said it was linear in time, but here, this is not linear in time. T is squared. So this is quadratic in time. Remember that word from algebra? Right? So what's basically going on here is that in the x direction, as time marches on, I'm getting the same number of meters away, 5 more meters away every single second, right? But here, because I start at 20, when a t is equal to 0 seconds, then this becomes 0 and I'm 20 meters in the air. But as time goes on, this becomes a 1 second. 1 second later, I subtract 4.9 meters from here, but then at 2 seconds, I subtract a whole lot more, and at 3 seconds, because it's squared, I subtract a whole lot more. So what happens in the vertical direction is I start off very close to the 20 meter mark, but then as time goes on, I'm basically covering a lot of ground really, really fast, because as time goes on, I'm subtracting much, much, much larger than, it's not linear. When it goes to 2 seconds, it's like 4 times what this number is. When it's at 3 seconds, it's like 9 times whatever this is subtracted, and so I hit the ground very, very fast. So it's linear in time for the x direction and quadratic in time for the y direction. Now, I'm not going to do this part of it, but if you solve this for time, which you can do, you just divide by 5, right? T would be x over 5. And then if you take that and you put it into the time position here, then you could see that if you solve for time, you're going to have an x, and you're going to put it in here, you're going to get an x squared. There'll be a number, 1/5, you'll have to square it and all that, but you'll have an x squared term. So you'll have a y equals some junk times x squared. Remember, we said a long time ago that when you have an algebra, y is equal to some junk times x squared, whatever it is, you're always going to have a quadratic. And notice that there is a minus sign in front of the quadratic term. That's going to make the parabola upside down. So we said in the beginning that when we throw things through the air, they form a parabolic path or a parabola. And now we're mathematically showing that this is true. Because the equations of motion, when you put them in place, you get a linear in time for the x and a quadratic in time for the y. If you solve this for time, you're going to get 1/5 times x. You're going to put it in here, then you're going to get an x squared term. Y is going to equal something times x squared with a negative in front. That is going to give you the upside down parabola shape. So I think now we can say that part 1 is solved, because the part 1 was just sketch a path. And now we know from the equations of motion that it has to be parabolic, so we kind of draw a parabolic shape. It starts 20 meters in the air, up here at the top of the building at 0, 20, 5 meters per second horizontally, and that's what it's going to do. All right, now part B says we want to make a graph of the x component of the velocity of the ball as a function of time. The velocity of the ball is a function of time. And then we're going to do the same thing for part C. We're going to make a graph of the y component of the velocity of the time. So what is the equation for velocity? We have this one here, but we want it as a function of time, so we're going to have to use this one. We're going to do the x direction first. So now we have to make this equation work for the x direction. So what we say is the velocity in the x direction is equal to the initial velocity in the x direction plus some acceleration times time. We just write the equation now, we put the x's in place. But in the x direction, there is no acceleration. It's just 0. So the x is going to be equal to the initial value of the velocity in the x direction plus 0. So that just drops away, right? So I guess you can put 0 for the acceleration times time. But then we realize, well, wait a minute, we already know what the initial value of the velocity is in the x direction. It's 5 meters per second. So we can just put it in here, and we can say that is, and at 5.00, I'll just put 5 here, and it's going to be meters per second. So if we want to make a sketch of this, what we're going to do is we're going to draw a little xy graph right here, x, y. And actually it's going to be, we're going to draw, it's actually as a function of time, sorry about that. This is going to be time, and this is going to be the velocity in the x direction. So what we're going to find is up here at 5 meters per second, it's just a constant number. So the velocity never really changes like this. So what this basically means is that the x component of the velocity, it's just equal to whatever we started with, and it never changes. There is no time in here at all. It's just always the same. So what I told you in the last lesson, that the horizontal and the vertical component are totally unrelated, and there is no acceleration acting horizontally, this is showing up in this result. Because all we did was write down the equation of motion, we put the acceleration to 0, and then whatever velocity you start with is the same velocity you have horizontally forever. When you kick this thing off at 5 meters per second, in the absence of any other forces, it's going to go this direction forever. The only reason it stops is because gravity is pulling it and it hits the ground. When it hits the ground, of course, everything stops. But if it never hit the ground, it would just keep on going, and it would keep on going and coasting at that horizontal speed. So of course, it really does stop eventually when it hits the ground, but in the absence of that, it goes on at 5 meters per second that way forever. All right? Now let's do exactly the same thing for part C, and let's make a sketch of the y component of the velocity here. So we're going to use this exact same equation, but we're going to tailor it for the y direction. So we're going to say the y component of the velocity is the initial y value of the velocity plus at. Plus at. But we now know that acceleration is, of course, negative v naught y minus g t. So basically we know that we need to know the initial velocity, and we know that gravity is 9.8 and it's acting downward and so on. What is the initial value of the velocity in the y direction? It's initially not moving at all down or up at all, so the v naught y is actually 0. So we'll just put a 0 here. We'll put a 0 minus 9.8 times time, because this is 9.8 meters per second. So vy is negative 9.8 times time. And this is going to give me a number in meters per second, of just like this one gave me in terms of meters per second. So how do we sketch that? What this is basically telling us is when time is 0, literally when time starts, there is 0 meters per second vertically. But 1 second later, we're traveling negative 9.8 meters per second down. But 2 seconds later, it's 2 times that velocity down. 3 seconds, it's 3 times that velocity acting down, and so on. So every second that goes on, you're going faster and faster and faster vertically downward. Whereas horizontally, you're not moving any different in speed horizontally. So if we could draw a picture of this, what would it look like? I think I'm going to need this down here as well. So this is time, and this is going to be Vy. So what we're basically saying is at 0 seconds, we're going 0 meters per second. So we're going to have a dot right here at the origin. And then we're going to have, 1 second, 2 seconds, 3 seconds. Let's call it 4 seconds. So 1, 2, 3, 4. And this is, let's call it seconds, right? So after 1 second, you're at negative 9.8 meters per second down. So you put a dot like right there. After 2 seconds, 2 times this is negative 19.6. 3 seconds, you're at negative 29.4. And 4 seconds down here, you're at negative 39.2. So at 2 seconds, you're down here at 2 times 9.8. At 3 seconds, let me get in front of it here, you're somewhere over here. And at 4 seconds, you're over here. So what do you have? This is not perfect because it's basically freehand, but you basically have a straight line going down through here. Now don't get wrapped up in the fact that it's a straight line. It doesn't mean that it's a straight line path. What it means is that as time goes on, the velocity is getting faster and faster. Remember, the velocity is how fast you're moving. So as time goes on, you're moving faster. And then another second later, you're moving even faster. And then another second later, you're even moving faster and faster and faster. Now, eventually, if you jump out of an airplane, the wind will start to make it where you can't speed up anymore. But if there was no air, you would just continue speeding up and speeding up and speeding up until you just splat into the ground. So this is a graph of the vertical velocity. All right, part D, at what distance from the foot of the building does the ball land? Now we want to actually calculate how far away this thing happens here, or how far away it actually hits the ground. Now the strategy here is we need to know, we want to calculate x, the distance the thing lands away from the ground. So let's try to write an equation for that first. So we're going to write this equation of motion down. It looks nasty and ugly, but it's actually, not difficult, because for part D, we actually already figured it out, really. When you look at what we did, we put the x direction down. We wrote the equation of motion down. We said the initial position is at x is equal to 0. There is no acceleration in the x direction. And so the position in terms of x, t seconds later, is just 5 times t. So we just write this down again. X is equal to 5 times t. So we can just say x is equal to 5 times t. All we need to do is figure out how many seconds later it hits the ground. If we knew, for instance, that it hit the ground 10 seconds later, then all I would do would be put 10 here for t, and then 50 meters would be how far it goes. Because basically, if you know how long in seconds it travels, and you know this equation, you can tell me how far away it's going to be that many seconds later. But the question is, how can you figure out the number of seconds that it's going to actually remain in the air? And we never calculated that. So we have to go back to basics and we have to think about it for a second. That was the horizontal motion of the ball. It's 5 times t. The vertical motion of the ball was given by this equation, the vertical position of the ball. Remember, we wrote this equation down and we said, okay, there was no initial velocity in the y direction. It started 20 meters in the air and it's accelerating downward. So basically, this is telling me where its vertical position is t seconds in the future. So how do we use this equation to figure out when it hits the ground? Well, this is its final position. It starts 20 meters in the air. When does it hit the ground? It hits the ground at 0 meters over the ground, right? Because it starts up here at 20 meters above the ground in the y direction. But when it hits the ground, it's at y equals 0. So all we have to do is use this equation and we put y is equal to 0 in here, and then we solve for how many seconds that takes. That's what we have to do. So let's write this equation down, which we already basically figured out from before. We wrote down before that y was going to be equal to 20 minus 4.9 multiplied by t squared. Let's just double check. 20 minus 4.9 times t squared. And now what we're going to do is we're going to put into the situation the fact that we know it starts at this high above the ground. Its final position is at y is equal to 0. So we put a 0 in here. 20 minus 4.9 t squared. We move the 20 over, we get negative 20, negative 4.9 t squared. We're going to flip it around and we're going to say that t squared is negative 20 over negative 4.9, right? And when we divide these numbers, 20 divided by 4.9, we're going to get 4.08. So what we do then is we say that t is going to be equal to the square root of 4.08. Of course, when you take a square root, it's really a plus or minus, but you can't really have negative time, so we just take the positive square root here. And so t works out to be 2.02 seconds. So what does this mean? It means we use the vertical equation of motion to tell us that when y, the position of y equals 0, that means when it hits the ground, it takes 2.02 seconds for it to hit the ground. So now we know it takes 2.02 seconds to hit the ground. We'll take this time and we'll stick it back into the equation for the x position here to figure out how far away it lands. So we now know that x is equal to 5 times t. So x is equal to 5 times 2.02 seconds. So this is meters per second. This is how far the fastest thing is going horizontally times seconds. What you're going to get is 10.1 meters. 10.1 meters. And so what this basically means is you're going to have this building like this, and the ball is going to be going like this, right? But what we have basically now learned is that this distance right here is 10.1 meters. And I drew the thing not to scale, but this is 20 meters tall. Of course, if we kick it faster than 5 meters per second, what's going to happen is, here's the thing you got to remember. If I kick it faster, it's still going to hit the ground in 2.02 seconds. Why? Because it's still dropping from the same height. And the time it takes to hit the ground has nothing to do with how fast I'm kicking it horizontally at all. Because look at how I calculated it. I used the vertical equation of motion. I didn't use anything about the horizontal speed. I just used this, 20 meters in the air, the acceleration 1/2 gt squared, and I solved for t. So if I kick it 20 meters per second or 50 meters per second or 1,000 meters per second, gravity is still pulling on it and it's still going to hit the ground 2.02 seconds. But if it's going faster horizontally, of course it's going to travel a farther distance, because if it was going 100 meters per second times 2 seconds, then it would be like 200 meters in the distance. So when you throw something horizontally, it does not affect how long it takes to hit the ground at all. But what it does is it travels more distance in the same amount of seconds that the thing is going to take to drop anyway. Even if you shoot a rifle bullet, it's going hundreds of meters per second. The bullet is still traveling toward the ground vertically at exactly the same rate. It's still going to hit the ground at the same amount of time that it would if you just dropped the bullet. The only difference is for a rifle, it's going to travel a lot of distance this way, horizontally, in the same amount of seconds that it takes to hit the ground. So I keep repeating myself over and over and over again, because the first time I learned this, it kind of blows you away that you can throw something 1,000 meters per second horizontally and it's still going to hit the ground in the same amount of seconds as if you just dropped it. But you have to get over that skepticism. You have to get over that, and you have to accept that that's going to happen. These problems, or this problem here, we treated it the way I told you we would treat it. We treated x and y separately. The x motion and the y motion are separate. We use the y equation to figure out how many seconds it took to hit the ground. Once we know the number of seconds, we put it back into the x equation to figure out how far it moved horizontally. That is going to be kind of a skeleton roadmap for how we handle all of these problems. So solve this yourself, watch it a couple times if you need to, follow me on to the next lesson, we'll continue to build your skills.